My name is Mike Martin. I teach at Seneca College, and I'm given the opportunity to introduce our speakers this morning. This is the third session in the morning. Because I'll make the announcements now that I usually do afterwards. Just one announcement: that following this session is lunch. Lunch will be in that room right across the courtyard there. The doors underneath those windows. Okay, so you can proceed over there. All right. Today this session we're going to talk about PCP and Systemtap. Our presenters are Lukas, Berk, and Jonathan Lebon. Lukas is a performance tools engineer at Red Hat, contributing to Systemtap since 2010. His work has included providing additional OpenJDK hotspot probe support and enabling Systemtap to natively probe Java programs. Jonathan Lebon is a York student, currently interning at Red Hat as part of the Systemtap team. He has worked on front-end improvements, such as making better suggestions on errors. He's presently working on making Systemtap work more easily with virtual machines. So I'll keep welcoming Lukas and Jonathan.
Hey everybody, thank you for the introduction. So as we alluded to earlier, we're going to be giving a talk on PCP and Systemtap. There we go. So quick overview of today's topic. We'll introduce the idea while we're here, give a couple demos, and let's go. So, we'd all appreciate and like if our software and systems ran perfectly all the time, but realistically, we know that doesn't always happen. You're probably spending, half your time debugging things or making sure that things work as they should. So we'll overview the 6 stages of debugging. Get the bug report, that can't happen, it doesn't happen. It quickly switches to, well, that doesn't happen on my machine. Okay, it does happen on my machine, that shouldn't happen. So why does that happen? Oh, I see why that happens. And how did that ever work? And if you're like me, there's 2 bonus here. Who wrote that? And you might know what's coming. Oh, I wrote that. So the first step is acceptance and admitting you've got a problem, but we're here to focus on steps 3 and 4. That shouldn't happen, and why does that happen? So hopefully we can get to accelerating through fixing it and deploying your fix. So in other words, our main objectives are early detection of a potential problem. If we can detect that we may have a problem before it actually happens, that's even better, so we can avoid the problem. And rapidly drilling down to pinpoint the issue. A lot of times you have very complex distributed systems. There's a lot of information at your disposal. Making sure you get the right information and use the right information is critical. So how has this typically been done? If you're a systems administrator, perhaps developer, you've got the typical logging tools such as rsyslog, syslognd, journald. So these are really just kind of accumulating totals of information. They're very linear, one way, and it's your job to parse through them all. You also have tools called top, iostat, vmstat. So these are kind of profiling tools or monitoring tools where you're given a set of information and it's not very malleable, right? Top provides you, say, with the processes and the CPU usage. If you want anything else, well, that's too bad. What if you want some more detailed information? You might use a mixture of scripting languages. If you're unlucky, you get a completely unreadable Perl script handed down to you, and you probably use these scripts to make sense of the first 2 items. This can be very hairy. We'd like a common set of language that you can use on all your systems. And the thing is, the specific tools vary by the system you're using across architectures, across operating systems. I'm a Linux fan. I want open source, but realistically, in your environment, you might not have just Linux. You might have, AIX or Mac OS or Windows. Right? That's a much more typical use case. And proper analysis requires more context. Simply seeing, I had a log message error or my Perl script pulled this bit of information. You need more than that. And you're going to find throughout this presentation that you need more information about those events, specifically, unit of time or if it's hertz or percentage, right? Simply a number doesn't do it. So we got the tool, you might guess, to solve this and introducing Performance Copilot. So a couple points of interest, what we like about this tool. It's got a Unix-like component design, meaning you got a lot of small programs that do one thing, they do them well. It complements your existing system functionality. Performance Copilot doesn't ask you to throw out everything you've got. It complements it and just kind of adds to it. Bless you. So we're not asking you to relearn everything you've ever learned. It's cross-platform, so it runs just about on every OS under the sun. You can get a full list at our website. Ubiquitous unit measurement. So again, I've said this before, it's going to come up again. I want to know if it's a percentage, if it's a unit of time, frequencies, it counts per second. That information is very important, and it's built in from the ground up in the PCP. And it's extremely extensible. We realize that we give a lot of great defaults, but you probably have some user space program that we don't know about, and if you want information from that program, that's most key, what you want to know, we've made it very easy to extend PCP into your own program. And that's open source. Yay for open source. So how does Performance Copilot work? How is it laid out? Well, in the most basic case, on one machine, you have two components. First is called Performance Metric Domain Agents, a big long name for basically saying, this is the small program that simply knows how to talk to the domain of interest, whether it be the kernel, your user space application, your network. This knows how to talk to that specific domain. And on the flip side of things, you have the Performance Metric Collection Daemon. This is the tool that knows how to talk to the agents, right? You'll have one of these in the box. You might have like multiples of the agents. So for easy use going forward, we're just going to call the first one the agents, and the second one the PMCD. It's a bit easier to say. So for the agents, you might have things, say, information on the kernel, your web server, Apache, and Nginx, your database management system, and network. There's more of these. We ship a whole set by default. It's just a sample. And then on the same system, you got your PMCD, and this is the tool that actually pulls the information in and out of those agents, right? So this isn't just on one system, but once again, we might be on a distributed enterprise solution where I've got a server in Australia because they don't want to come all the way across North America for the information. So we work that in. We've got the agents communicating with the PMCD, and then we got clients that pull the information out of that. So we got PMIE, PMStat, PMVal, PMChart, PMInfo. Like I mentioned before, Unix-like component design. Each of these tools I'll give you a bit of a demonstration on, but they do one thing, they do them well, and they pull the information out of the PMCD. Great, so we got the agents, PMCD, and clients, and this is what I alluded to earlier. And the remote PMCDs will feed into the clients, right? So I can come up from Australia, Europe, what have you. Is that all making sense? So a couple useful commands. You install PCP. What might you want to do out of the box? Well, there's PCP. It just gives you a brief summary of the installation on that particular machine. You can do PMStat hostname, and that's just a high-level overview. So it's kind of like a combination of the tools we saw earlier, such as top, IOStat, VMstat, and PMChart. And it's a configurable metrics chart. So once again, depending on what you're looking to measure or diagnose or analyze, it changes. This GUI is very flexible, and it can change the information displayed based on what you want to look at. I'll demo it in a second. So a couple example outputs, PCP. This is the output it'll give you. A lot to parse through, but the idea is, you get an overview of your system. You can see the time zone. So once again, if it's across the world, you got the PMDAs. So these are the agents, right? In this typical case, I'm interested in the PMCD itself, proc, Linux, a few more to name. These are what's configurable. Every machine might look different in that sense. And you have the logger instance. PMStat, so this is the overview. Notice I want to get information from multiple hosts. So I have Toyum, Earth, which is my little server box, and Saturn, which is one of my workstations. It'll give you a readout, what node it is, the average load, memory, swap, and this appends, right? So every second or so, you're going to see a readout like this, just kind of giving you a high-level overview. And it'll keep appending as you go, as long as you let it, right? This is a sample PM chart. I've configured this one to show the CPU utilization. The middle section is network I/O, and the bottom is memory usage. So a couple things I want to draw your attention to. At the very bottom, again, units of measurement. We're doing this in seconds. If you want a larger sample, it might be hours. It depends. You got start and stop, so you can play back live data, or you can do this over a log file if you want to see things happen from a log. Again, units. So we have an idea of what this is measuring. Gigabytes, megabytes a second, and percentage. So here I ran a program on my machine called stress. It does exactly what it sounds like. It just stresses your box out. And you notice I've got a spike in memory usage and CPU usage. Just to give you an idea of what's going on in the system. And here, on one of my virtual machines on the machine, I ran a yum update. So there's a lot of I/O traffic on the network. At the same time, you might notice a trend, say, the interrupt context on the CPU is higher. So, these are great overview tools, but I thought at the beginning we said, you want more than that. You want more than an overview. If I'm going to do this, why not just use top, say? Well, we have the technology. So what PCP does is we basically have what's called performance metrics namespaces. And what that means is a subsystem-based hierarchical naming scheme. So because you have a lot of information available to you, you have a lot of things you can try and find the metrics from, what you want to do is be able to organize this properly. So this is what it might look like, your whole tree of information available to you. This is how it works. If I want to say, look at the network, TCP, receive packet metric, so you go network, TCP, receive packet. That's what a typical naming scheme would look like. It can change based on CPU usage or what other agents you have available to you. So how do we make use of these metrics? Well, pminfo-f is something you can just run quickly, and it'll give you a list of absolutely every metric that you have available to you. I would suggest running this through less because there's a lot of output. So pminfo-t-d and the metric name. So you pinpointed something you're interested in, and we're going to give you kind of a help, like what is this metric actually measuring, because there's a lot of them. And once you find a metric you're really interested in, pmval, what is this metric right now? So a couple sample outputs, pminfo-t-d, kernel all sys fork, and you don't know what that is? Well, it's the fork rate metric from procstat. And it'll give you some information, say it's the 64-bit unsigned integer, and the units, again, is counts. So I've got a metric I'm interested. What's the actual value? Well, if you do pmval disk all write, again, it'll give you a very quick overview in case you've forgotten. And notice we've converted it here to counts a second. So you can change this depending on the metric, and you're going to get a list that just kind of appends to it as you go. So individual cases, great. What do we do with it? So again, this is our layout so far. Well, PMCD will then talk to a tool called PMIE. We'll get into this more in a second, but this is where some really powerful stuff comes into play. And if you have metrics that you want to log for later, we use PM Logger, and this will create log archives. This is the typical logging that you may have seen before. The same data, it'll work for the last 10 years. Will work on the current clients as well. So that's very important to us. We don't want any difference between the data you can use 10 years ago and the data you can use today. But for PMIE, so PMIE, the Performance Metrics Inference Engine. What is it? Well, it allows you to form metrics-based expressions for evaluation. Right? This is how you gain real insight into what the metrics are telling you. So it's language that you can see ratios from the metrics, counts, aggregates. You can do percentiles. So everything in the 90th percentile, the disk writes. I want to see something happen. So what happens if your machine is writing like crazy? You can raise alarms, log entries, shell commands, name a few. What's important is you can run this on live data. So you can have this on your server box and you get a notification that we've got a problem, or you can run it kind of post-mortem on logs to test the rule that you're going to write and see if it would have triggered it, or just to see statistical trends within your data. And you can run these rules across multiple hosts. So if you've got 3 machines doing X across the world, you can find out on all of them. So let's take a look at a couple possible examples. Disk all write divided by disk all total times 100. You might guess that that's the percentage of all disk operation are writes. Right? So you can kind of get a sense on how you're going to use these rules. Disk dev total, so that's the operations total on the device. If it's greater than 10, so if it's more than just booted up. And the disk dev write is greater than the disk dev read. All right, so you can combine expressions to form more powerful rules. And So how would you use these type of rules? Well, say, what if you want to know that your Ethernet has stopped functioning, right? This is a possible scenario. But verbose, but let me give you a rundown. You've got some conditionals. So you say some instance, this is almost like an if statement. So if we have an instance matching ETH or EM, which are your typical Linux Ethernet delimiters or names. So if the network interface total errors is greater than 10 a second, again, you can specify the time. Then we want to write to the syslog, we got Ethernet errors and the number of errors. All right, so a quick demo on how this might actually work in the system. Can you all read that okay? Sounds good. So I've written a rule called load demo. So the basic gist of the rule is the 1 minute load average exceeds 1 times the number of CPUs on your host. This isn't a realistic rule you'd use in real life. You'd probably want to amp that up a little bit. But you see in the second line, the hosts, I want to run this on my local host. Again, we can run this on multiple hosts. The delta is going to be 10 seconds. Realistically, you'd have a higher delta. You might have spikes you don't really care about, but for the sake of demo. And then on the high load, on some host, again, you can run this on multiples. On the kernel, all loads, so all processors, on the hosts of interest, for the 1 minute load average, is that greater than the number of CPUs on this machine? And if it is high load average, are you stressing out again? So to demo this, I'm going to run a tool called stress, as I mentioned before. And all stress will do is run a set number of CPU processes that are very intensive and it will stress out the machine. So to start, the journal is just like the syslog entry, essentially. And just going to grep for PCP, make life a little easier. And so this is the rule loading, PMIE-C, which is the configuration. I'm going to run it in the background for you. And to actually run it out, so see stress, you see the rules and loaded. Stress 20 CPUs, tasks, and got time out of 60 seconds. We should hopefully not actually hit that. Cool, so we're dispatching 20 CPU cycles. Give it a little bit. You'll see it pop up at the bottom here. Ooh, no. So PCP, PMIE, high load average, or you're stressing out again, right? So you can see how you would extend this to, say, your application, your systems. Hopefully this will help you sleep a little bit more at night. Won't get those alarms at 4 a.m. So cool. So as I mentioned earlier, we want to be able to extend this tool as much as possible to your user space application. So a bit of a quote, if it is important for monitoring system performance and you can measure it, you can easily integrate it into the PCP framework. Someone famous, the PCP user guide. So there's several ways to extend PCP to your advantage to your user space application. You can write your own agent, right? So this is the program, just the small little bit that talks to your program. You can write your own CLI or GUI interface, so something like PM chart that will extract the proper information in the way you want it. Or directly add sampling and tracing instrumentation. This is a bit outside the scope of the talk, but we have plenty of documentation on how to programmatically do these things. It's all on our website. Any quick questions before we move on? Yeah? Right now, it's just typical unit sockets, and on my systems, I have Avahi running. So you can either give it the IP address, or it's just typical Unix sockets in that sense. Port 44321. We're adding that. That's like latest release coming up type deal. We've got a lot of effort on that right now. Anybody else? Okay. So at this point, we've hopefully detected a potential problem, hopefully avoided it, but hey, identified the possible culprits. But how do we know what's causing the issue, right? We've seen the issue happen, but we got to drill down a little bit further. And for that, Jonathan's going to let you know.
Hello, everyone. So I'm going to talk to you about Systemtap. So as Lucas mentioned, he talked about PCP and how it can help you just monitor the health of your whole network. So at the same time, it can help you whenever something goes wrong, pinpoint really quickly where exactly something has gone wrong. So in that sense, Systemtap is kind of like the second half of that story. It helps you, do some more detailed investigative work to find out what exactly is going wrong and how you can fix it. So what is Systemtap? Well, normally the tools you would use for fixing bugs, would be stuff like tracers, profilers, or debuggers. Now, the thing is, tracers, for example, limit you to function calls, and sometimes they can give you information you don't want, right? So they can overload you. Profilers are nice, but the simple ones are just too abstract, and the more intricate ones require a lot of setup. Debuggers, of course, are the ultimate tool, but it's not always an option to, stop the program, change the source code, recompile, stuff like that. So Systemtap kind of fills the gap between all of those. It allows you to write scripts to observe all sorts of events on your machine, system-wide, live. So if you know dtrace, it's a similar idea to dtrace. So how exactly does it work? Pretty much you write a Systemtap script, and then the script gets converted into a Linux kernel, a Linux module, a kernel module, which then gets inserted into the kernel, and then you just get data back from the module. So the reason why Systemtap is so powerful is because we're in the kernel. That means we can see pretty much everything that happens on the system. So just imagine, you kind of know where something is going wrong. You've pinpointed kind of the trouble spots in the source code, and you want to find out more information about those spots. So the basic structure of a Systemtap script reflects that. So you pretty much have a trigger and a handler. So the trigger is whatever you want to monitor for, whatever you want to watch out for, and the handler is what you want to execute when the trigger is fired. So to give a simple example, for example, hello world. So here we're just triggering whenever the begin probe is fired, which pretty much happens when the Systemtap session is started. And all we do in the handler is just print hello world, pretty straightforward. A more realistic example is, process.begin. So whenever the ls process is started, we just print ls was started. So if you've never used Systemtap before, I mean, even just that is pretty cool. You get to detect whenever ls is started, no matter from where, or yeah, on the whole system. We already saw process.begin and begin, so those are pretty basic probes. But Systemtap supports a lot of different types of probe points, which triggers or probe points. That's the Systemtap lingo for triggers. So the more useful ones are the kernel and process probes on statements and functions. So for example, here we're placing a probe at the statement located in the sysread function at this specific line in this file. So you see, you can be very precise at where you want to place your probe. So this probe will fire anytime the kernel goes over that line of the code. In this probe, we want to detect every time the main function of ls is entered. So the key thing to note here is Systemtap can do both kernel space stuff and user space stuff. And in fact, nothing stops you from writing a script with both of them together, which means that it allows you to do probing throughout the stack and really just follow everything that happens all the way down. We also support Java method probes. So for example, you can fire a probe anytime a certain method matching a specific pattern is called in a specific class name in a certain PID of a Java process. Other noteworthy types include perf probes if you want to use performance counters, hardware performance counters. Timer probes if you want to, for example, fire something every 100 microseconds, regardless of where you are in the code. Net filter probes if you want to react to network events. SDT marker probes. So those are useful if you place probes inside of your code, like in your source code. And yeah, so you can explicitly say where you want to place the probes. So we give you the include file for that, and you can just pop it in. And in fact, this is also compatible with dtrace marker probes. If you already use those in your code, that's Systemtap can use those as well. So if you want to list all the supported probe types of Systemtap, you can just do stap -- dump probe types. So in fact, I can do that right now. No. So these are all the types of probes that Systemtap supports. So we talked about the timer probes, and you got a lot of stuff here. So I would encourage you, like, before you write your script, just take a look and see what could interest you. It's really a wealth of possibilities. So the language itself, the Systemtap language, is pretty straightforward. It's what you would expect from a scripting language. So you've got your variables, your conditionals, your loops, your functions. So pretty much if you've programmed in any high-level scripting language before, you should be fine. You should be OK. So there's a few things that are more specific to Systemtap. So we have tuple-keyed arrays, which pretty much means that you can have arrays that are not just indexed by an integer, but by 2 integers, or an integer and a string, or whatever you want, And then you also have for each loops, which kind of are special loops to iterate through those special kinds of arrays. You also have aggregates, which are pretty much sets, which allow you to collect sets of numbers and then just perform statistical operations on them, like min, max, mean. You have macros. If you know C macros, it's the exact same idea. So pretty much identifiers that are expanded to something else during the parsing stage. And then regular expression matching if you want to check if a string matches a regular expression. So the really powerful thing about Systemtap is that it allows you to access context variables. So what does that mean? So for example, here we're probing for the syswrite kernel function. So this could correspond to the write system call when you're doing your C coding. And whenever that probe fires, you can actually have access to whatever variable is local in that point of the code. So if you want to find out what are those variables that you would have access to, you can use the -l option of Systemtap. So here I just do stap -l kernel.function syswrite, and it'll tell you, okay, this is the function, this is where it's located, line 516. And if you do probe this function, you will have access to the file descriptor, the buffer, the count, and ret, which is just a local variable. So the fd, buff, and count, if you see, those are pretty much the parameters that you pass to write, right? So I mean, it's pretty powerful stuff. So the -l notation in general, it's good to just figure out what are the probable functions. So here we're doing process ls.function star. So star pretty much means all the functions. So if I actually run this, so I'm just going to cat it first to show you, right? It just does that. So these are all the functions that you can probe in the ls process, right? So I mean, just to give you a simple example here. So for example here, rev strcomp a time. Right. So it's telling you that if you probe that function, you'll have access to the A context variable and the B context variable. Okay, so Systemtap comes shipped with tap sets, which are pretty much like it's pretty much analogous to a library in other languages. So what do they contain? One of the major things they contain are probe aliases. So what does that mean? For example, as we saw before, instead of probing the kernel.function syswrite call, you can just do syscall.write. So what is the advantage of that? Well, depending on what kind of system you're on, the write system call won't always map onto the syswrite kernel function call. So instead, you can just do syscall.write, and that'll, on whatever machine you're on, that'll try to catch the kernel function that corresponds to a write call, let's say. So in that sense, the probe alias kind of allows you to abstract away the differences between architectures and make your script more portable. So tap sets also contain helper functions. So for example, here we're probing syscall.write, Anytime that happens, we use the user string end function to retrieve whatever string is located at the address buff and cut that off and only print the first count number of characters. So of course that'll only work if it's a string, right? Maybe it's just binary data. But I want you to notice here, right, buff and count, they're the context variables we saw earlier. They're just the parameters that were passed to write. But the more important thing is, this is really powerful stuff. It allows you to catch or intercept all the write system calls through the whole system. I mean, that gives you a lot of things to play with. The tab set also includes helper variables. So for example, here, again, we're just probing syscall.write. And instead of trying to look at each individual parameter, we just use the argstring variable, and that'll just give you a nice little printout of all the parameters that were passed to write in string format, instead of just trying to hunt down all the different parameters. So if you notice here, there's no $ in front because that's just a normal regular variable, a Systemtap variable. It's not a context variable.
So would that be more than one string or just one string?
Oh, it's one string with all the parameters concatenated in string format. So you would have like fd, buff, which would probably be the address, and then the count.
So does that mean that this library knows the right way to format and stuff?
Yeah, I'll get into that. There's another, yeah. So, okay, so other useful tab set functions. So retrieving strings, we saw that with user string n. Retrieving main and function arguments. So for example, if you have the process, if you're looking for anytime the main function of ls is entered, you can use the command line string function, which will pretty much print out in a pretty human readable format what were the parameters that were passed to ls. So in fact, this is not specific to main. You can call that from other process probes, but anyway, yeah, it'll print out the arguments passed to ls. Here, we're catching every time the open file function of nano is entered. And so here we use this notation, so that addresses your question a bit. So we have $, $2 in front, and $2 in the back, and we use parms. And what that pretty much means is print all the parameters that were passed to the open file function in a human-friendly format. So for example, if they're strings, try to print out the string. If it's a strut, try to follow the members and print out the members of the strut, stuff like that. I'm not sure. I'm not familiar with that trace. So.
It does its best to, in this case, just print out the parameters of that function. What do you mean specifically like strace, though? Yeah. Yeah.
Exactly.
So that's exactly what this does.
Yeah. So other useful task functions, if you want to retrieve the name of the probe point or the function probed, so let me explain that one. So here we're probing all the functions in ls, right? So I use the star notation. That means it's going to fire anytime any function in ls is called. So of course, whenever it fires, you want to know what function was actually fired. So for that purpose, you have the pp and the pp-func function. So pp will just resolve to the full name of the probe point. So for example, if main was fired, it's going to contain a string containing process ls.function main. On the other hand, pp-func just holds the name of the function alone. So if it's main, it's going to just be main in string format. If you want to issue a system command, you can use the system tab set function. So here, anytime main is entered, we just spawn echo main started, Okay, so another cool thing with Systemtap is the -x switch. So let me explain why that's really useful. So here we're probing all the right system calls, right? Now, of course, that's powerful stuff. You can see the whole system, but most of the time you're going to want to be focusing on a specific process, right? So what you would do in that case is you can pass the PID of the process you're interested in to Systemtap with the -x switch. And then when you're in your Systemtap script, that will end up in the target function. So whenever target is called, that just returns this PID that you passed with the -x switch. So we have target function, and then the PID function returns whatever is the PID of the process that did the write system call. So what we're pretty much doing here is whenever a write system call is performed, check if the PID of the process who did the write is the same PID as the one we're interested in. And if it is, then print, use user string n to print like whatever the user was trying to write. So using just this simple technique, you can filter out all the noise and just focus on what you want. So now I'll show you a couple of Systemtap examples. So Lukas talked earlier about stress, and now he used it to stress his CPU and memory. So, how does stress work? What functions does it have? And when you do something like stress --CPU3, where does it spend its time stressing the CPU? So those are the kind of questions that Systemtap can easily answer. So the first question, what functions does it have? Well, we saw that already, right? You can just do stab-l process stress dot function and use the star notation. So in fact, if I do this, so I'll just show you the contents of this, so you know exactly what I showed you, and then so these are all the functions that are in stress, So okay, not a big list, maybe 10, 12 functions. So that's pretty cool. The cooler question is, where does it spend its time stressing the CPU? So for that, we can write a very simple Systemtap script. So I'm going to go through it line by line with you. So first, we declare two global variables, funcs and cur. So funcs is pretty much going to be an array, and cur is just going to be a string. So I'll show you what they're for. So the first probe we place is to catch all the function calls in the process, in the stress process. And all we do in the handler is just pick up whatever the name of the function is using the ppfunc tapset function we saw earlier and put that in the cur global variable. Okay, so if main is fired, cur will become main. Here I kind of cheat because I initialize cur with main, which is not technically true, because if you look at a trace, main is not the very first function, but it's good enough for first approximation. So then the second probe we place is a timer probe, which will fire every 100 microseconds. And all we do in there is increment the value of the element associated, of the array element associated with the function. So, for example, if we're still in main, then the value at funcs main will be incremented. So at the end, what we're going to have is funcs will just be an array full of functions as the key and the amount of time spent as the value, right? So in that way, you can kind of think of funcs not as an array but a map, but it's pretty much the idea. So then at the end, we use a probe end, or an end probe, which pretty much gets fired whenever the Systemtap session is ended. So all we do in the handler is we use a for each loop to traverse the funcs array. And here, if you notice, I have a little minus sign after funcs. So that pretty much means I want to iterate through the array in order of decreasing value. So that means the function where we spent the most time will be printed out first, right? And then in the actual loop, we just say, we just print out how much time was spent and the name of the function. So if I actually run this, I'm pretty sure it's 6. So again, I'll just show you. Right, so I'm just running the stab script, which is the 6.scp, which is what was on the slide, and then I use the -c switch. The -c switch is pretty much the same thing. You can think of it as the same thing as the -x switch, where you assign a PID instead, except that here Systemtap actually runs the command for you and assigns the PID of the resulting command to the spawn command. So that's why if you saw in the script, I just did process dot. I didn't have to specify what process it was because I used the -c switch. So let's just run it. So here all we're going to do is we're going to run stress on 3 CPUs or 3 instances for 5 seconds. So it's running, and then it gives us a printout. So these lines are from stress itself, and these lines are from the Systemtap module, right? So it's telling us that, okay, of the 5 seconds that we ran stress for, 4.997 seconds were in a function called hog CPU. Okay, sounds pretty believable. 3.9 milliseconds were spent in main, and 3.4 milliseconds were spent in fprintf, probably when it was printing those two print statements. So the point here is, oh, actually, normally that one doesn't show up, but yeah, 100 microseconds in atol_s. So the point is here, with very few lines of scripting, you can get very rich information back, you know. And in fact, if you notice here, I haven't written the word stress once in the whole script, right? So that means you can use this script with any executable you want, and it'll give you the same printout. Of course, it would have to be like a C or C++ program where you have debug info on the functions for the executable. Okay, so now I'll show you a second example, which is a little more involved, but it really shows you the power of Systemtap. So here we've got a really simple C program. So let's just focus on main first. In main, all we do is we call next number int max times. Okay? And then next number, what does it do? It just returns 0, then 1, then 2, etc. Right? Now there's two things to note. First of all, next number returns a short. Okay? That means counter will always be between short min and short max. The other thing is, in main, we call next number int max times. So what does that mean? What could happen here? Exactly, right? So if you're on a system where a short and an int are the same thing, you'll be safe, right? You won't call next number. Your state variable will never overflow. But otherwise, your state variable will wrap around before its time. And that'll give you a negative state, which can have disastrous consequences, right? Just imagine just scale this idea up to a huge program, and you know, you get into an invalid state, that's just the end, right? So here, just for the purpose of the demo, we've added 2 lines, which just pretty much prints out a statement anytime state is negative. Of course, if you're writing code and you have these lines, that means you're thinking that state could be negative, so you take the precaution. So that's why I add these lines after. So just imagine it's part of a way bigger program. You know, you can't just stop it, fix it, and recompile. It has to keep running. So how can you make sure that you never end up in an invalid negative state? Well, that's the perfect job for Systemtap. So how can you use Systemtap for something like this? Okay, so we just need to place 3 probes. Okay, the first probe, we place it at the statement at line 13. Does anyone remember what line 13 is? That's okay, I don't either. So line 13 is line 13 is where state is assigned the next number. So this probe will fire after that line is executed. So state would have just received its new value, right? So we can use that probe to keep track of the state. The second probe, we use it to intercept whenever the next number function is returned, and we watch out for an invalid transition. So again, right, just process my app.function, and then notice .return at the end to mean I don't want this to fire when we enter the function. I want it to fire when we return the function, when we return from the function. Okay, and the third probe is when we enter the next function. So it's pretty much the same thing without the .return suffix. And it'll make more sense in the script, but we'll use it to reset the counter. So let me show you the script now. So first we have 2 global variables, state and reset counter. And then we have our first probe from the previous slide, and all it does is, you know, pick up the new state from the context state variable and put it in the global state variable. And then the second probe we saw, which is when next number returns, we just check if the return value is negative. So here again, right? Notice the $sign in front. So this is a context variable. It'll be the value that next number will return. So all we do here is check if it's negative, because we don't want it to be negative, right? We check if it's negative, and if it is, then we say, okay, invalid state detected. We're about to go from this positive value to that negative value. And then this is where the true power of Systemtap shines. You can modify the context variable. So we're like, stop it, set return to 0, you know? And then we set reset counter to 1. And the reason for this is that in the next probe, which is fired whenever next number is entered, if reset counter is 1, we also reset the counter context variable. So the reason for this, if you remember the C code, it's so that whenever the return value is negative, we not only reset the return value on the spot, so that state is never assigned the negative value, but we also make sure that when next number is called the next time, it's going to be, the counter will also be reset to 0. So we'll restart from 0 and up. So how does this work in practice? Okay, so again, I got to remember. So first I'm just going to recompile the program. Can never hurt. So in the bottom window, I'll just run the application. So if you remember, we had print statements that would print out something anytime the state was negative, right? So that's that print statement. So it's pretty much showing us that state is going into the negatives, right? And then here, I'm going to run the Systemtap script. So here, I'm going to use the -v switch, which means verbose, so give me more output. And the -g switch, which pretty much means allow me to modify context variables, because you might not always want people to be able to modify it. Anyway, I won't get into it, but G stands for guru mode, and it means I know what I'm doing. And then, so now let's start the Systemtap script. So what will happen is, as soon as the module is inserted, Systemtap will intercept any time the state is about to go into an invalid state and stop it from happening. See? So right away, it stops printing out invalid state because we catch it before it goes into the negatives. And then Systemtap tells us, invalid state detected, about to go from 32,000 to -32,000. And in fact, if I stop the Systemtap script, bam, it starts going back into invalid state again. Start it again, and we're happy. Sad, happy. Right, it's just an example, but depending on your application, right, you would have something more complex. Maybe you're checking for the index of the array not to be negative or out of bounds. It just depends on your application. But the big point here that I want to focus on is that, okay, let me just so Lucas's laptop doesn't freak out. So the big picture here is that, first of all, we're able to inspect context variables. And on top of that, we can modify context variables. So this gives you really awesome power to do, all sorts of really neat stuff, right? And I mean, this has been used to fix, zero-day security holes, just as like a temporary fix until a real fix comes out. And that's it. Any questions? Yeah.
The debugging you just showed looked a lot like something to do with GDP, but I'm sure this is more powerful and more interesting. What do you actually do? What do you play with when you're actually using that instead of developing? How do you use that?
Well, I can only speak for me personally, but for example, so what I've used Systemtap for example, is I was writing another application, which is actually which is going to be part of Systemtap soon, and for some reason, another process that I was relying on was creating a file using the wrong permissions. So like, okay, let's use Systemtap and try to see what if it calls umask to set umask to something different, and maybe that's why and just like that, I place a probe right before the file is created and see what the umask is at that point in time. So I mean, that type of stuff you can't do even with GDB. I mean, I have no clue what the program does. I mean, how the program works internally, right? So it would be a hassle to go through the source code and like try to understand all the stuff and step through all that stuff. So Systemtap just right away, I can do that much more quickly.
In comparison as well to GDB, you have to again like stop the program, look at it, then recompile it. This could be on a live system, right? That could be like the machines at Circ or whatnot, and you can't stop it, but you got to fix it until you can redeploy.
Well, you don't have to stop. Well, yeah.
The program.
Right, you could attach.
Yeah, I mean that program was still was spinning away, right? We didn't stop it.
But you need to have compiled it. You need to have compiled it.
Right.
Yeah, debug info needs to be available, right? If you're on, say, a Fedora system, if you install the debug info packages, say it's not a program you've written, you install that, you can then change the state there, see how it's interacting with your user space program.
My
We do a very good job at catching things like inlining and optimizations. Let us know if you missed something.
I was inferring heavy into because my abort report, the trace backs seem to have optimized out. System happens to understand that.
This is work across all architectures, or is it specific to certain architectures?
We support a lot of architectures. I don't know if all of them, but
Not all of them, but I mean the big ones. So anything that we relationships with, we support. So like x86, what is it, Power, AI, not AX, sorry, AI64, I believe still, S390. There's active work being done on it right now.
it's at arm's length.
Yes.
All right, bad joke, bad joke.
The type of fix-ups that you had there, where you intercept that variable with an editing value, can you do that against the kernel as well as?
Yes.
Yeah.
Yes, you can. Yeah. Right.
I have a kernel lockup situation, and I know where it's locking up, so it would be very interesting.
Yeah. Tell us your story after.
Tell us your story here.
Any other questions? Okay.
Thanks, guys. If you want to get in contact with us, this is where you.
I'd like to thank Jonathan for a really interesting talk. And
Thank you very much.
And,
Thank you very much.
Oh, no problem. So, like that. Cool.
Thanks.
So lunch, like I said, is across the way, and thanks again. That was good.